Classification of matter. We classify things all the time, and scientists are big into classifying things. If you think about vehicles, right, you can classify them according to, well, this is a semi-truck, and this is a regular truck, and it's a pickup truck, and a sedan, and a subcompact car. You could classify them by how many wheels they have, by what type of fuel they use, by how many doors, by what color they are. Lots of different ways to categorize things. And so we'll see that in science as well, that we have different, different ways of classifying things. So matter, what is matter? Matter is anything that occupies space and has mass. So the bench is matter, your body is matter, has mass and occupies space. What about the air in the room? Does air occupy space? Yeah, it does. You can fill a balloon with air. The air holds the balloon out, right? You put air into the tire of your car. It occupies space. It's not as obvious that air has mass, but it does. If we're talking about a specific instance of matter, a particular kind of matter, we call that a substance. So we can classify matter in different ways. We can look at what state it's in, the physical form, or we could look at the composition. What are the components that are making up the matter? And so we'll look at both of these. Classifying according to state, there are three main states of matter: solids, liquids, and gases. And each of these states has different properties. So I don't know what this green substance is supposed to represent. It kind of looks like Jell-O or something there. It's a lot easier to talk about water, though, because water is something that we are familiar with in all three of its states. When water is a solid, we call it ice. When it's a liquid, we just call it water. And then we also experience water in the gas state. So this is you're boiling water on the stove, and there's steam, okay? That's water in the gas state. We know, because of our experiences with water, that the way to convert something from a solid into a liquid or a liquid into a gas is to heat it, right? Get it warmer, and it will change its state. These illustrations here show the relationships between the particles, the individual molecules or atoms, in the different states. So here in the solid state, the particles are very close together. And this isn't animated, but those particles are not moving relative to each other. So we can also talk about the three states of students. And currently you are in the solid state. So the person who's been sitting next to you was sitting next to you 5 minutes ago, and they're probably going to be there in another 5 or 10 minutes, right? You are not moving relative to each other. Later today in lab, when we check into drawers, we'll all be milling about. That's the liquid state of students. So here, the particles are still touchingly close, but now they're moving relative to each other. Are these particles in the solid state, are they motionless? No. They have movement, they're just not moving relative to each other. You all are moving, aren't you? I think everyone's at least breathing, right? Somebody might be sleeping. I don't see anybody sleeping yet, but you're moving, you're breathing, you might be fidgeting or taking notes. Particles in the solid state do that. We think of it more as a vibration, wiggling back and forth. So they do have movement, but they're stuck relative to each other. Here we've got the liquid, and then in a gas, what's different is that now there's a large amount of space between the particles. So this is like when class is over and you guys effuse out the door and you go off in your own directions and you maybe don't see anybody from class until the next class period. So here the particles are very far apart and they're not interacting with each other at all. So this is a lot of what I just said, but with words, so I'll go through this fairly quickly. So in the solid, the molecules are close together in fixed locations. They're vibrating, but they don't move around relative to the other atoms. So as a result of that, a solid has a fixed volume and a rigid shape. This calculator's a solid, right? If I put it in this basket or if I put it on the counter, its shape or its volume doesn't change. It stays the same. We can categorize solids in different ways. We'll just look at two quick ones here. Crystalline versus amorphous. So in a crystalline solid, something like this diamond, there is a regular, repeated three-dimensional pattern to the particles. It's a crystalline solid. So right now, in the student section here, those of you that are sitting around the benches, I would say that you're in the crystalline mode because you're sitting in rows, right? And then along the edges, we have some amorphous students, right? Because they don't have chairs, and so they're just kind of randomly arranged around the back wall. Amorphous means without shape. So this would be something like glass, plastic, rubber. It's not obvious just looking at it, but the particles in it are not arranged in a regular repeating three-dimensional pattern. So liquids. In liquids, we still have things packed closely together, but now those particles are free to move relative to each other. Because of this, the shape of a liquid will change. Its volume is fixed, but the shape can change. So if you take a glass of water and you pour it into a bowl, the shape of the liquid water changes. Its volume is the same though. Because they move relative to each other, liquids have the ability to flow, and that's what makes them able to change their shape. In a gas, there's a lot of space between the particles. So here we have a solid in a piston sort of arrangement and a gas. In the solid and also in the liquid, because the particles are touchingly close, you can put pressure on this piston and you can't compress them any further. They are already as close as they can be. Whereas with a gas, because there's a lot of empty space, if you put pressure on the piston, you can squeeze the particles together. You can change its volume. So lots of space between the gas particles. They're free to move relative to each other, and so gases are compressible. Their shape and their volume can change. They will take on the volume and shape of their container. So that's classifying according to the three physical states. We can also look at the composition of matter. What is it made up of? So this is a flow chart that summarizes what's going on with this classification scheme. So here's matter. We can put it into two broad categories, a pure substance or a mixture. And the question we would ask there is the composition variable or is it fixed? A variable composition is a mixture. There are two or more different substances mixed together, and you could have half and half, or you could have 25% and 75%. The composition can vary. In a pure substance, the composition is uniform throughout. So water is composed of hydrogen and oxygen atoms, but every water molecule has exactly one oxygen and two hydrogens. It's a fixed proportion, okay? So that makes water a pure substance. We can take pure substances and divide them into compounds, such as water, where the individual particles, the molecules, can be separated into simpler substances. You can actually break water molecules into hydrogen and oxygen using a 9-volt battery. Drop a 9-volt battery into a cup of water, wait a couple of minutes, and you'll start to see little bubbles form. It's electrolysis. It's taking the water molecules, breaking them apart into hydrogen and oxygen. You can do that with a compound. With an element, it cannot be broken down into simpler substances. So here the illustration is helium in this Goodyear blimp. So helium is composed of helium atoms And you can't make them any simpler than that. They are already as simple as they can be. So those are pure substances. And then over here under mixtures, is the mixture uniform throughout, or is it kind of chunky? Does it have layers? Are there different parts in it? If it's uniform, it's homogeneous. If it's not uniform, it's heterogeneous. So if we look at wet sand, well, there's the water and there's the sand. It's two different things, right? And you can see the difference. So imagine taking a glass of water and putting a couple of tablespoons of sand in there and stir it up. Imagine what would happen, right? The sand is going to sink to the bottom. And you can see there are distinct differences between those parts. If you put sugar in water and mix it up, the sugar dissolves and mixes thoroughly and forms a homogeneous mixture. You have a question?
So like oil and vinegar in a cup would be heterogeneous, right?
Yeah. Oil and water would be heterogeneous because they won't mix together, right? They're going to form two different layers. We use a lot of prefixes and suffixes in science. We use those in the English language too, but you might not have really paid much attention to them. The prefix hetero means different, so a heterogeneous mixture has different parts. And homo is a prefix that means the same, so homogeneous means it's the same throughout. These illustrations are also helpful when we talk about, well, what's a mixture, what's a pure substance? So if you look at these two examples of pure substances, you could notice that all of the particles are the same. In here we have atoms, this one we have molecules, but all of those molecules are the same. In a mixture now, we have two or more different kinds of particles. Here, all the water molecules are mostly together and the sand molecules are together, but there's two different kinds. Here, we've got the sugar and the water, and they're mixed up really well, but if you could zoom in, I really wish we could zoom in and see molecules. That would make things so much easier. If we could zoom in and look at that, we would see there's two different kinds of particles. That makes it a mixture. Okay, now we're going to go through all of that real quick. So the first division between pure substance and a mixture. So here's where kind of the definitions and words are. So pure substance, only one component, and its composition is invariant. It can't change. A mixture is composed of two or more components, and the proportions can vary from sample to sample. You could have a cup of, 2 cups of sweet tea, but one might be a lot sweeter than the other, right? Because you put more sugar into it. Those are mixtures. Take those pure substances, categorize them into elements or compounds, and this is based on, can the substances be broken down or decomposed into something that's simpler? The element is something that cannot be chemically broken down into simpler substances because the atoms are the basic building blocks. So think about Legos. Can you take an individual Lego brick and break it into smaller ones? Not really. Some of the really long, skinny ones, if you tried hard, you could break them, but generally Lego bricks, you can't break them, right? Atoms are the building blocks of elements. They cannot be broken down into something smaller. A compound, though, contains molecules. And that can be broken down into something simpler because you could separate that into the individual elements. Water is hydrogen and oxygen. We can separate them through a chemical change into hydrogen and oxygen. Most elements are chemically reactive, and we do not observe them in nature as free elements. They usually combine with other things. So, I don't have an example. The mixtures, heterogeneous versus homogeneous. And again, we've got prefixes here. Hetero meaning different, so it's got different parts. Homogeneous, the same, it's uniform. In the heterogeneous, we've got multiple substances whose presence can be seen, sand and salt mixture. You can mix those together, but if you look closely, you can see the little sand grains and the little salt crystals, right? Think of mixing flour and pepper together or something like that. You can see the different kinds of things in there. If we're talking about soup, I hope you guys got lunch. If you had chicken noodle soup or minestrone soup, it's going to be heterogeneous, right? There's the broth, and then there's the noodles and the chicken or the vegetables. There's different pieces in there. If you had a cream soup, like cream of tomato soup, or a clear broth, now that's still a mixture, right? There's different things. It's not an element. There's no element called tomato soup on the periodic table. It's still a mixture, but it's uniform now. The tomato soup is the same at the top and the bottom. You don't see any pieces that you could separate out. So the tomato soup would be a homogeneous mixture. Sweet tea is another example. That's what they call it in the South. Sweet tea, not sweetened tea. The reason homogeneous mixtures have uniform composition is because the particles mix uniformly. They mix on a particulate level. Mixtures can be separated. And this is actually a whole branch of science, separation science, of how to separate stuff. We can separate mixtures because the two individual components, or more components, have different properties. And so we can make use of differences in their properties to separate them. A very simple method that we will be doing in lab is called decanting. So how would you separate water and sand? You've got a bucket with water and sand in it. Well, you could let the sand settle to the bottom and then carefully pour the water off of the top, right? Now, can you get all the water off the sand? No, but you can get most of it away from the sand. And you've separated the sand from the water, right? That's called decanting. Another separation technique is called distillation. This is how distilled spirits or liquors are made. So we could imagine in here we've got a mixture of liquids with different boiling points. Maybe it's ethanol and water, alcohol and water. To separate those, they're both liquids, it's a homogeneous mixture. You can't just pour one off because they're so mixed together, but their boiling points are different. So you can heat the mixture and the ethanol will boil first. When it boils, it goes from the liquid state into the gas state and will go up the neck of this flask and try to escape. But instead of just letting it go off into the atmosphere, we're going to collect it, run it through a condenser that's going to cool it and cause it to become a liquid again, to condense, and then it's going to run down here and we're going to collect it in another flask. And so we can separate the alcohol from the water. The water has a lower boiling point. If we have a solid and a liquid, we can use filtration. Decanting is nice, but it can be pretty finicky. Filtration is usually much faster. And you've probably all done filtration in the kitchen. If you've ever made a pot of spaghetti and poured it into a colander to drain out the water, you did filtration. If you make coffee at home, not the instant kind, but real coffee. Yeah, pour over. So we actually have a coffee maker. It's called a Chemex, and it looks like a filter funnel, and you put the filter paper in there. You mix the coffee and the water, and then you pour them in here. The coffee goes through the filter paper, the liquid coffee, the good stuff, and the grounds get trapped behind. So filtration is a way to separate solids and liquids.